In this video, we will learn how to identify a selection of aqueous negative ions based on their reactivity and the color and solubility of their salts. In chemistry, qualitative analysis can be used to determine the identity of an unknown chemical. We can use chemical tests to identify the different positive and negative ions present. During a chemical test, a chemical reaction will take place, and we might observe a number of different changes. Heat might be given out, we may see a color change, or a gas might be produced. We could see some bubbles in the test tube, which is referred to as effervescence, and we might even smell a peculiar odor. Finally, we might notice a solid being formed inside the test tube, which we refer to as a precipitate. Anions are negative ions and sometimes referred to as acidic radicals. If we were to imagine a common acid, such as sulfuric acid, with the hydrogen ions removed, we would be left with a sulfate anion or acidic radical. When we test for acidic radicals, we use a specific order and methodology to do so. This helps us to accurately identify different ions. We first use a primary test, and if the result is positive, then we follow up with a confirmatory test to verify the primary one. We use specific reagents in a fixed order when testing for unknown acidic radicals, and the order relates to the stability of the different anions. Firstly, we use dilute hydrochloric acid, which will help us to identify carbonate, sulfite, bicarbonate, sulfide, thiosulfate, and nitrite anions. If the unknown anion has not been identified using dilute hydrochloric acid, we move on to the second testing reagent, which is concentrated sulfuric acid. We use concentrated sulfuric acid to identify halide anions and nitrate anions. If, having used dilute hydrochloric acid and concentrated sulfuric acid, we still don't know what the identity of our unknown anion is, we finish by using aqueous barium chloride solution, which will help us to identify sulfates and phosphates. Let's look at some of the observations we would expect to see with some of these tests. We can use dilute hydrochloric acid to test for bicarbonate, sulfide, thiosulfate, and nitrite ions. And in all these cases, the dilute acid is added to a solid sample of the unknown salt. Bicarbonate ions react with the acid to produce carbon dioxide and water. We can test for the carbon dioxide gas produced by using lime water, which is a saturated solution of calcium hydroxide. The lime water will turn cloudy or milky in the presence of carbon dioxide. However, carbonates also react with dilute hydrochloric acid in the same way, so we need a confirmatory test to tell us that this particular unknown anion is specifically a bicarbonate and not a carbonate. For this confirmatory test, we will use a solution of magnesium sulfate. When we mix a solution of magnesium sulfate with a compound containing bicarbonate ions, then magnesium bicarbonate will be present in the test tube. However, if carbonate ions are present, they will instantly react with the magnesium ions to form the insoluble magnesium carbonate, which would form as a white precipitate. The second stage of this confirmatory test is then to heat our solution. This causes the thermal decomposition of the magnesium bicarbonate, and once again the formation of an insoluble white precipitate of magnesium carbonate. So, using this confirmatory test, we can see the difference between a carbonate and a bicarbonate salt. Carbonate ions are present if the white precipitate appears instantly. Bicarbonate ions are present if the white precipitate appears only after heating. We can also use dilute hydrochloric acid to test for the presence of sulfide anions. The sulfide ions react with the acid to form a gas known as hydrogen sulfide. Hydrogen sulfide gas has the horrible smell of rotten eggs, and while that might give us a clue while performing the test, using smell and sniffing unknown gases is incredibly dangerous, and so smell, even if it is very informative, is never a part of formal qualitative analysis in chemistry. So, what we use instead to test for the hydrogen sulfide gas is a solution of lead acetate. We take a small piece of filter paper and soak it in the solution, and hold it carefully above the test tube. When the gas comes into contact with the lead acetate, a further reaction takes place, and lead sulfide is formed on the piece of filter paper. Lead sulfide has a characteristic black color. The confirmatory test for sulfide ions is the use of a solution of silver nitrate. And once again here, we form a black substance. This time, silver sulfide, which is a black precipitate, forms inside the test tube. When we use hydrochloric acid to test for the presence of thiosulfate anions, we need to look out for a yellow precipitate. The yellow precipitate is solid sulfur. But we also get another strange-smelling gas generated here, which is known as sulfur dioxide. It's important to remember here that the sulfite anion also generates sulfur dioxide, so it's the yellow precipitate, or solid sulfur, that tells us in this primary test that we are dealing with a thiosulfate anion and not a sulfite anion. We can test the sulfur dioxide gas coming off using filter paper that we've wetted with potassium dichromate. Potassium dichromate is an orange solution, and when reduced by the acidic sulfur dioxide gas, turns from orange to green. While the production of the pale yellow precipitate is a very good indicator when testing for thiosulfate, we also need to perform our confirmatory test. One of the characteristics of the thiosulfate anion is that it is able to reduce iodine to iodide. An iodine solution commonly has a dark brown appearance, and when mixed with a solution containing thiosulfate ions, the iodine is decolorized. Nitrite anions can also be detected using dilute hydrochloric acid. During the reaction, a chemical known as nitrous acid is produced. This acid is unstable and decomposes, releasing nitrogen monoxide gas. In turn, this gas reacts with oxygen in the air and produces nitrogen dioxide, which has a characteristic orangey-brown color. The confirmatory test for the nitrite ion involves passing the orange-brown nitrogen dioxide through a solution of potassium permanganate. We acidify the potassium permanganate with concentrated sulfuric acid, and as the acidic nitrogen dioxide gas passes through this solution, the characteristic deep purple color of the permanganate is lost and replaced by a pale pink, almost colorless solution which contains manganese 2+ ions. As we follow our testing methodology, we move from testing with dilute hydrochloric acid to testing with concentrated sulfuric acid. If, having tested with both of those acids, we had still not managed to identify our unknown anion, we would move forward to the third stage of testing and begin to use barium chloride solution. Barium chloride solution can be used to test for phosphate and sulfate anions. The first step of this test is to add some barium chloride solution to the unknown solution thought to contain either phosphate or sulfate anions. If either of these two anions are present, then a white precipitate will form, either barium phosphate or barium sulfate. In order to differentiate between these two similar white precipitates, we add some dilute hydrochloric acid. When we add the acid to the white precipitate of barium phosphate, the white precipitate will disappear. The solid barium phosphate reacts with the acid to produce phosphoric acid and dissolved barium ions. This reaction will not take place with barium sulfate, and the white precipitate will remain. The confirmatory test for phosphate anions involves the addition of silver nitrate solution. When silver cations come into contact with phosphate anions, a precipitate of silver phosphate is formed, which has a yellow color. As we did before, we can dissolve this precipitate by using either nitric acid or ammonia solution. If we use nitric acid, we form silver nitrate and phosphoric acid. And in the case of the ammonia solution, we form a silver complex. Before we summarize what we've learned about further tests for anions in this video, let's take a look at a question. The image shows a series of tests carried out on an unknown sodium salt X. What formula is the unknown sodium salt likely to have? In this question, we are told that an unknown sodium salt is being tested with a series of chemical tests. In the image, we see that the sodium salt is dissolved in a solution. Based on the tests used and the results of the tests shown in the provided image, we will need to determine the identity and chemical formula of the sodium salt X. Moving from X to the left, silver nitrate is added to the solution containing X. The result is a black mixture. Let's suppose that the salt X contains sulfide ions. After adding silver nitrate, the sulfide ions present in the unknown solution will react with the silver ions from silver nitrate. The result of the reaction is the precipitate silver sulfide, which is black in color. The result of the test with silver nitrate suggests that X contains sulfide ions. Let's continue to record the chemical reactions occurring in the remaining chemical tests. When hydrochloric acid is added to a fresh sample of the solution containing X, a smelly gas is produced. When hydrochloric acid is added to the solution containing sulfide ions, a chemical reaction occurs between the sulfide ions and the hydrogen ions from the acid. The reaction results in the formation of hydrogen sulfide gas, or H2S, which has the unpleasant odor of rotten eggs. According to the diagram, when lead-2 acetate is added to the mixture that produced the gas, a different black mixture forms. If there are still sulfide ions or hydrogen sulfide in the mixture in the test tube, then a chemical reaction will occur with the lead-2 acetate. The products of the reaction are acetic acid and lead-2 sulfide, or PBS. Lead-2 sulfide is a black precipitate that gives the mixture in the test tube its black color. The results of the 3 tests shown in the image give evidence that the sodium salt sample contains sulfide ions. Therefore, the identity of X is the salt sodium sulfide, which has the chemical formula Na2S. What formula is the unknown sodium salt likely to have? Na2S. Let's summarize what we have learned about the further tests for anions. Dilute hydrochloric acid, concentrated sulfuric acid, and barium chloride solutions can be used to identify unknown anions. Dilute hydrochloric acid is a primary test of carbonate, sulfite, bicarbonate, sulfide, thiosulfate, and nitrite anions. Concentrated sulfuric acid is the primary test used for halides and nitrate anions. Barium chloride is used as a primary test to identify sulfate and phosphate anions. We use confirmatory tests to verify the results of primary tests.